Assalamu alaikum. My name is Rashid Mubasher, and I worked on this project titled Harassment Connections on Fiber Bundles. This is a topological analysis, and we will be focusing on some mathematical applications of this framework. My supervisor is Dr. Tuba Feroz. About this project, the inspiration comes from a very key observation, which is in theoretical physics. We know from Einstein's theories that gravitational field can be described in terms of curvature of space-time. This is very interesting because it raises a natural question, which is whether other physical phenomena can also be described as some sort of a curvature of some other object. And to explore that, we're going to go into depth with this project. And it turns out that in order to answer this question, we need to understand what curvature means and what that other something could be. Curvature will be explained later, but the other something turns out to be a very important mathematical object called fiber bundles. And so majority of this project addresses all of those questions. In particular, the three things we focus on are whether moduli spaces can be presented as principal fiber bundles. Moduli spaces are spaces of solutions of differential equations. And then we'll look at how algebraic invariants are related to curvature 2 form, which is a way of expressing the curvature of your manifold in the language of topology. And then finally, using all of that, we will define some differentiation operators on general manifolds, which will extend the notion of directional derivatives. And the applications will be explained later, but I've highlighted them here. In particular, we'll be able to calculate geodesics without any underlying metric. We'll also be able to apply this to a very applied area of mathematics known as neural networks, and we'll see how this framework helps us understand the lost landscape of neural networks. And finally, a more typical example would be when we do population dynamics modeling. Those are systems of ODEs, and we'll see that this framework also addresses key questions in that framework. So, starting with a little bit of a review of Riemannian vector bundles. Whenever we have a manifold, think of a sphere or the surface of a donut, which is mathematically called a torus. To each point on that sphere or that manifold, we can attach a tangent space. For a sphere that looks something like this, it will be a tangent plane attached to each point. This helps us give meaning to the notion of vectors on a manifold. See, vectors have to be straight line objects. They must exist in vector spaces and not necessarily on a curved manifold. And so tangent bundles, tangent spaces allow us to generalize the notion of vectors. Therefore, it will help us generalize the notion of directional derivatives, which rely on directions of vectors. Collection of all of these tangent spaces is called a tangent bundle, and that structure is a prototypical fiber bundle. Fiber bundle simply being an extension of this idea where to each point on the manifold we attach any arbitrary object, not necessarily a vector space. So in this case, when we have vector bundles, which is a special case, we get a very special theorem from Riemannian geometry which says that every Riemannian manifold admits a unique torsion-free connection, which is called the Levi-Civita connection. Later on, we'll be generalizing exactly this notion to fiber bundles. Before we go to fiber bundles, however, we must understand three important mathematical concepts. First is the notion of differentiation. What does it mean to differentiate something? Differentiating something means comparing it at two neighboring points. However, notice here that the vector space attached to one point and the vector space attached to another point are different mathematical spaces. You cannot compare objects from one to the other. So we need one notion of taking objects from one vector space into another one. That is called parallel transport. And parallel transport is simply a linear combination of the vectors in this space as expressed in basis vectors of the next space. That's represented mathematically here. This linear operator will be extended to have two further properties. We will require it to be Leibnizian linear in the first argument, which means it should behave as if this is a linear operator of the first argument, but Leibnizian, which means it should obey the product rule in the second operator. This collectively makes it into a differential operator. As soon as you have a differential operator, you can see whether it commutes when we change the various inputs. Two natural commuting operators are the following. The first one is called torsion. We won't be talking about this too much. However, the second one is crucial, which is called the curvature. Now, the key mathematical insight here is that curvature, that the set of vector fields on any manifold forms a Lie algebra. And so curvature can be seen as a Lie algebra, can be seen as a way to check whether the derivative operator is a Lie algebra homomorphism. In other words, this can be represented more compactly as this if the curvature is 0. And if curvature is not 0, then there will be additional terms here which will show that this fails to be a Lie algebra homomorphism. Using all of this, we can now jump onto a more abstract setting where we can't visualize things anymore. We go onto fiber bundles. For fiber bundles, the motivation comes, the generalization comes because for instance, in theoretical physics, such as particle physics, what we typically do is we study symmetry groups. One of the symmetry groups, which is very commonly studied, is the U1 cross SU2 cross SU3 subgroup, and that's associated to the standard model of particle physics. However, in order to study this group, this group is not a vector field, a vector space. So when we're studying this group, we're not attaching vector spaces to manifolds, we're attaching groups. And so we want to generalize the idea that instead of a vector bundle, we have something called a group bundle, which we call a principal bundle, which I have mentioned somewhere around here. Yes, so the principal bundle is one where the fiber is the group itself. Now, just to visualize this very quickly in a simple example, I've presented the following one. Suppose you have a circle, which mathematically we call the S1 space. To each point on the circle, you may attach a straight line. So, for instance, a copy of R, the real line. You have two choices to do that. Either you can just attach all of the lines in the same orientation, or you can attach some lines in one orientation and some other lines in other orientations, and that collectively gives you two different choices of constructing what we call the total space. This one, because we're making a trivial choice of just attaching the same thing, this associates to the trivial symmetry group, while here we're allowing ourselves to flip the lines once, so that will correspond to the symmetry group being Z2, which means you allow flipping of the lines. And in both of these very simple examples, we get remarkably different behavior. In one case, we get a cylinder type object, which is very easy to study, and it's got it has a flat curvature just like the normal R2 plane. However, in the second case, we get a highly complicated object. It's not orientable and has interesting topological properties. All of this is useful. All of this is fairly simplified. However, we can apply this to a lot more complicated situations as well, such as to get the Yang-Mills equations. If the symmetry group was no longer Z2, but this whole complicated group, then the resulting equations will be Yang-Mills equations, which are central in mathematical physics and theoretical physics. Now, all of this theoretical framework was a pedagogical review. Now we go on to the final three applications of this work, which is, first of all, we have metric independent geodesics over vector bundles. What does that mean? We know what a geodesic is. By definition, it is just a curve whose tangent vectors satisfy the following coordinate-free equation. This coordinate-free equation, we cannot solve. This is a differential equation, but we can't solve it this way. So we have to convert it into a coordinate version, and then we get to solve it. But notice, at no point here did we use the metric. These Christoffel symbols don't have to be defined using a metric. If you define it using a metric, you're going to the simpler case, but in general, on general fiber bundles, it doesn't have to come from a metric, and therefore we have generalized the notion of geodesics even on spaces where we don't have a canonical metric. For example, the neural networks. A neural network is simply a collection of neurons, and the main purpose there is to have a loss function, which can be mathematically seen as a scalar valued function of multiple variables, and we want to minimize that loss function. We want to find the parameters which minimize that loss function. In many ways, that's like trying to find the minimum point of a valley from any general starting point. However, in the case of neural networks, we don't know what the starting point is, and so the idea is to start from any arbitrary point and get to the minimum point without knowing what metric to use, without knowing what's the shortest path on this manifold. And so the previous application follows through, and we find how to get geodesics without having a canonical metric. And finally, we have this application where we notice that population dynamics and population models can be represented as systems of ODEs. And these ODEs, their solutions, are, well, functions, and that collectively forms an embedded submanifold of various functional spaces, for instance, L2 spaces. All of those spaces together, being manifolds, will have curvature properties. They will have fundamental groups. And by studying those, we can extract key topological data and impose conditions on that to improve the initial models. Now, just to quickly wrap this up, I'll mention two main points where we can extend this work further. And the first one is that all of this was presented in the language of tensors. However, a more unifying language in differential geometry is that of differential forms. And that's called the Cartan formalism. And it's very useful in when studying things like spinors. And so one possible extension of this work is to re-express this in terms of Cartan formalism and then take it forward. Another extension which is very useful is to relate this more thoroughly with theoretical physics. In theoretical physics, we observe that both quantum field theories, which I've presented a little bit here, and general relativity follow the same underlying theoretical framework. They're both differential geometry-based theories based on gauges. And so one could try to find more elaborate links between the two and therefore make progress in both of those areas. I'll finish off by just mentioning a few of the references, some of the textbooks and one of the papers that I've mentioned. And over the time, I shall be presenting some more work on a simple URL that I've made. Thank you.